A problem from section 2.4 in the intermediate algebra textbook. We're looking at page 104, number 47. So we're told a student drives towards school at a constant speed After a while, she gets a flat tire. She has to stop to fix it. And then she slows down to a slower constant speed. After a while, the police car, a student drives towards the school at a constant speed. After a while, she gets a flat tire, which takes some time to fix. She then continues to drive towards the school, but at a faster speed to make up for lost time. So we are to sketch a qualitative graph that relates the distance from home to the number of time or minutes. So we're sketching a qualitative graph. The distance that she is away from her house depends on how long she's been driving. So that's our time. And then this is our distance. So she's driving at a constant speed. So as she's driving at a constant speed, she's getting further and further away from her house. But she's going at a constant speed that's going to take her away from our house, which is we know it's linear. And then she gets a flat tire. So when she stops to fix the flat tire, time continues, but she's not getting any further away, nor is she getting closer to our house. After the tire is fixed, then she needs to start driving again at a constant speed, but she's moving at a much faster rate. So this is a little bit exaggerated, but notice that this constant rate is steeper because she's moving faster. So she's getting further away from her house quicker. Well, while this is steep, or it's some steepness, it is not as steep as this line. So that's number 47. This is the qualitative graph of the scenario where a student drives towards school at a constant speed, and then she has a flat tire. She needs to stop and fix her tire, and then she continues on towards school, but moving at a faster speed. Remember, it's a qualitative graph because it doesn't have any numbers. We know that her distance away from home depends on how long she's been driving. So T is our independent variable, D is our dependent variable. Another problem from the same section is question 41. I'm going to bring the book over, because it is a graph. All right, sorry, so you don't get motion sick. So we're looking at question 41. R is the annual revenue in millions of dollars of a company at T years since 2000, right? So years since 2000. This would mean that this is 2002, this is 2008, etc. A reasonable model is shown. What's the slope of the line, and what does it mean in this situation? Well, to find the slope of this line, we very simply want to pick 2 points that are right on the lines, like our intersection. So I'm going to say this point here and this point here fall so that we don't have to estimate them. Remember, slope is a change in y over change in x. So from here to here, we went up 5, and then we went up another 5. So we have a total change in y of 10, and we have a change in x of 2, 4, 6. What that tells us is for our slope, our m, which is our change in y over change in x, is 10/6. Okay. So to answer the question, our slope is 10/6. Make sure we note that it's negative. So we have a slope of negative 10/6. And what it tells us is that the annual revenue is decreasing at a rate of 10.6 millions of dollars per year. We know it's decreasing because we have that a negative slope. So the slope of this line is negative 10.6. What it means is the annual revenue for the company is decreasing at an average rate of $10.6 million per year. The reason we say it's an average rate is because they tell us it's a reasonable model, so we know that it's not exact. And here it is in words. The annual revenue for a company is decreasing at an average rate of $10.6 million per year. You could do the math if you wanted to and find it's 5/3, or decreasing at a rate of approximately $1.6 million per year.